Hi everybody, this is a quick update on our work on the Sala variability in crowded fields. It is a task force in the TVS, and this is an update of an original presentation made in Naples and then in Lyon. The first title was preliminary results, and now the update basically it's not so preliminary results. So the goals at the very beginning were to create metrics to determine the success of the LSST pipeline. So we have basically we have a sample of images in the galactic bulge, and the goal was to basically to recover the variable stars. So this means periods, magnitudes, eventually distances, and precision on astrometric solution. But to be frank, we were able to accomplish the first two goals because the other two requires much more efforts. And also the goal was to identify the best code for the science requirements, our science requirements, that is primarily pulsating stars. So this is a list of the people involved. We have our spokesperson, and she's Kelly Amberton, then a lot of people that probably you already know. And we started to organize our work by weekly calls, in which we discuss the past week's results and planning the next week. And that was the original timeline, but of course it's completely out because in principle we were supposed to complete our task in June. We started in February, and now we are in September, but in October, but we have a lot of new results, so we are happy of that. And in the framework of the LSSD data release, we are here. So we have at the very end of the process, in which we have the characterization of the objects, multi-epoch, that is object enforced sources, photometry of recognized variable stars. At the very beginning, we had the need to pick the ideal benchmark for our experiment. So we thought that we needed a robust, high quality and deep data set affected by severe crowding, and that allowed us to have time series photometry, of course a large field, and hopefully level 3 data product that is already processed images, because we wanted to bother in pre-reducing the available images, and also with a catalog of already known variable stars, just to have a comparison for our results. And the best case was in the galactic bulge, and we found this data set. The PI is ABSA, and as far as I know, the data set was planned to be a benchmark for LSST. So that was the ideal case, and it is made of more than 50 epochs with per band in 5 bands, with exposure that goes from 10 seconds to 100 seconds, if I remember. And the project was designed to detect RRSS. That is exactly what we needed. Moreover, we have already known variable stars from Ogle, and we can calibrate at least one piece of the data set with the Deccan plane survey. So this is the distribution of the fields in the SA data set, but also we discovered other data sets. They are very interesting, and we are planning to download this data and perform the same analysis. So it is a huge data set at the very end. So we identified a subset of only 150 mosaics that resembled, not staked, and we focused at the very beginning on R and I bands, but we added the G band. At the beginning, we selected only these CCDs because they hosted a higher number of known RRL stars. So at this preliminary stage, we decided to fully focus on only a single CCD, this one, to perform a deeper analysis. And when we started our experiment, the LSST pipeline was not robust enough to have a good comparison. I don't know, Colin, if what is the status now. So we adopted a completely blind analysis approach, and this means a preliminary total star reduction, full automated PSF photometry, so no visual inspection of the PSF. And to test our procedures at the very beginning, we focused only on the R-band images, then we added the G-band. To be done, the photometric calibration. Then we performed the search for variability on the basis of basically of the Stetson index, that is the spread of the photometry, and the fast Fourier transform power spectrum. The candidate variables were then analyzed to search the periods with the Fourier analysis and the PDM, and then we cross-matched with the OGLE, and then we visual inspected the light curves. So these are the results. This is the Stetson index as a function of the instrumental magnitude. And we have PSF photometry, a somatic solution. This is the preliminary catalogs of bona fide stars, more than 200,000 stars in only one CCD. And as I told you before, we adopted as a variability criteria the Stetson index, and with a minimum number of measurements. Then we ended with 4,000 candidate variables. This is again one of the checks that we perform on the photometry. This is the sharpness of the PSF as a function of the magnitude. The plot is quite good in comparison of the crowding, so we are happy with that. And this is the Stetson variability index again. And more or less, this is the envelope which is dominated by the photometric uncertainty, and all the sources above the envelope are candidate variable stars. So we performed a fast Fourier analysis to check the periodic variability and find the preliminary periods. And with this approach, we ended with only less than 500 stars. Then we performed the PDM period search. The first results were in the OGLE catalog. We had in this field 9 RRL stars and more than 100 eclipsing binaries, and we were able to recover only 8 RRL stars, but just because one was cut by the 15 measurements 0 point, we had 30 eclipsing binaries fully detected, and 23 with less than 15 measurements or undetected. And the others are cut by the adopted criteria. So the question was, which stars are we missing? And this is a plot of let me see, because yes, this is the power spectrum as a function of the sectional variability index, and color-coded is the photometric error. And basically, we are not able to recover this kind of stars. That is the stars with a small amplitude in the variability. So we were able to detect variable stars with a variability excursion larger than more or less 0.1 magnitude. These are some examples of the recovered light curve. This is an Ogle variable. This is a new one that was not included in Ogle catalog, so we discovered a new variable star. This is another one. This is a typical eclipsing binary. The period is not perfect, so you see that some data points that are duplicated at the same phase. And then we performed to overcome the problem of the small sensitivity with a full overall frame reduction. This means a better determination of the centroids and a deeper reference catalog. At the very end, a better photometry. And again, we recovered RIS stars. We started to do some experiments on the cadence, maybe by adding other available data sets. And especially this point, we searched for new and faint variable stars, and we started experiments with other techniques, the sectional variability index, the fast Fourier, but also other indexes. So these are some results with the dual frame photometry. We have an improved photometry, more robust variability detection. Now this is the number of the candidate variable stars. It's proved by a factor of 5. We performed variability search with automatic light curves and then the visual inspection. And well, this is to be done, but we already performed in the G band, and then we still have to face the calibration problem. This is the color magnitude diagram. This is R versus G minus R in only one chip, and these are more or less 100,000 stars. Color-coded is the photometric accuracy, so we are really happy because even in such a crowded field, we have a very good accuracy at the faint level. This is more or less 0.01 magnitude. And this was exactly the same field reduced by Sala. The scale is a bit different, and these are calibrated magnitudes, while this one are instrumental magnitudes. And you can see that at R20, we are able to recover more or less this kind of stars. So we are happy of the results. The CMD is not corrected for differential reddening, so it can be improved. So we had a catalog of almost 2,000 variable stars, a clean set of 100 stars with reasonable or good light curves. And this does not necessarily mean that the other candidates are false positives, because in some cases we had the wrong period from our analysis, and so the light curve was not, let me say, focused. When you have the wrong period, you have a small, some points here, other here, but they are not correctly phased. So I see the light curve and I say, okay, this is a mess, this is not variable stars. But that's not necessarily true. And this was an example with the PDM. This is an Ogle variable star recovered by our photometry, but with the wrong period, so the wrong phase, with the PDM and the fast Fourier transform. And so we performed the same analysis with this is the Lomb-Scargol. Lomb-Scargol was able to recover the correct period, but we also developed a new algorithm which is basically a focusing of the light curve. And it is basically the same result as the LOM schedule. The funny thing is that this is another RRI star, an Ogle one, so we know exactly the period from Ogle, and this is, the period is completely wrong with the PDM and the Fourier transform, but also, you see, with the LOM schedule. And with the new algorithm, the light curve was recovered. In this case, it was really difficult because we completely missed the rising branch of the light curve. And the algorithm is able to recover this correctly, the period and the light curve. So, let's go to the conclusion. In our opinion, excellent quality PSF photometry is feasible even in deeply crowded fields. And after 24 years, all frames is still the reference for the PSF photometry for point sources. We were able to automatically detect the variable suns and retrieve good periods. And we are planning experiments with the Scarlet, which is the LSST, the blender, if I may be able to install it on my computer. And I think that the comparison, I don't know if Colin shares my view, is that the comparison between the all-frame and Scarlet results could be of great interest for the people involved in LSST pipeline. On a parallel track, we started to think about an independent long-term project. So that this means mining the CAM archive, put all the stuff together and get a deep view of the bulge, a wide view of the bulge, but we have to face the problem of the calibration and a long-term view of the bulge because we have 4 years baseline data basically, but we are talking of this number of mosaics, and this is the number of individual CCDs. And this means fully automatic procedures and a lot of disk space. This is a meeting about the cadence. And of course, as already pointed out by Giuseppe, no doubt that in 10 years, SAR will be able to get all the pulsation parameters of the pulsating variable stars. This means periods, amplitudes, magnitudes, mainly RR stars. But the experiment on the cadence is to answer this question. What is the best observational strategy to get these parameters in a reasonable time before my retirement, basically? This is my reference. And we can perform experiment on a real data set with almost the same characteristics as LSST, as the pixel scale, the deepness of the field, and so on and so forth. And you're also planning with Marcella Ilaria to perform experiments with theoretical models in all, and with Giuliana in Bologna, in all the LSST passbands in order to understand what is the best filter to retrieve the pulsational parameters. Okay, that's all. Thank you.
Some questions?
Thank you for the talk. I think it was a very nice result. But I wanted to know if the search for variables was done only using one band in this case. Yes. So.
In this case, we use only and for example, most of those detections.
Of course. So these 123 eclipsing binaries were detected using only one band, right?
123 eclipsing binaries on the basis of the OAPa.
Okay.
We were able to detect a fraction.
Okay, more or less. How many with this cadence?
Other lines that are not included in the OAPa. More or less because it basically takes into account the fact that when you are going to the wrong phase, you have the same phase jumps. This is not, this is good for
Of course. Yep.
you can face as you want most of the time.
Okay. Thank you.
So this was taking each image and separately reducing it and then doing a catalog merge across all of the epochs?
We focused on the and our plan was to perform individual analysis
Right.
and then project into a common system.
Right. So I think there's a few interesting other steps I can think of to go on top of this. One would be to build a coad of that CCD. I hope if all the pointings are aligned, that might be easy to do if all the CCDs line up. If they're all dithered around, that gets a little bit harder, so I understand that. But if you do build the coad, use that to identify your centroids, and then go back and do force photometry on the individual epochs, you should, theoretically, that has to reduce the noise because now you're no longer worried about centroiding on individual measurements. You have a high precision centroid and you just get the flux of each. So it is force photometering, essentially.
This is for
Oh, well, cool. Okay, that solves that.
because
Yeah.
you have a huge uncertainty to be
That's what I was worried about. So that's solved. Second point is just that you said you just mentioned the Scarlet deblender. I just want to say a word or two about that, which is that this is. I should phrase this as this is the start of the LSST deblender. It is a new effort. It is something that we built in order to have a generalized way to describe the deblending problem, where you might want to impose different types of sort of scientifically meaningful constraints that we couldn't do before we had a way that sort of incorporated all these possibilities. So it is the framework, but it has not had these sort of years and years of tuning and perfecting that something like DAOFO or Allframe has. So one should not take it as like this is the final answer, and if it doesn't work, then let's throw it away. It's the start, and we'd like to know how to improve it. So that's really what's valuable to us.
This is going to be probably one of the topics of the discussion that we are going to have after the coffee break. Just to continue on your claim, one of the byproducts of the analysis performed by Massimo is that you are going to have staked images in all the bands that you are taking into account and on the individual images of the same band, because they have already been transformed in the same geometrical reference frame. So this means that when Massimo performed the analysis with Allframe, is using the position of the stars coming from the individual images, and after that, on the basis of the residuals, you can perform another iteration taking into account the residuals that are in the staked residual images. So this means that this is the way that we are recovering the completeness of the catalog in the Allframe environment. So it is crucial to have the staked images exactly for this reason. It has not been performed yet, but is one of the possibilities that we have.